Hi, we'll be talking about quadratic functions here, and this is actually the last review topic on mathematical techniques for the e-learning space. So anyway, let's start. For this refresher topic on quadratic functions, it is also split into two parts. In part A, we'll go through the review part and to solve some application problem sets about taxes and subsidies. Whereas in part B, we will discuss the remaining problems about perfect competition and the treasury of the commons, which are related to quadratic functions. All right, so let's start with the recall part in part A. The quadratic equations here. So we have several methods to solve quadratic equations. Our three methods are listed here. The first one is factor method. Suppose you have the quadratic equation x squared minus x minus 2 equals to 0. If you're working with the factor method, what you're trying to do is to factorize this quadratic equation. As you can see, it can be factorized into x plus 1 multiplied by x minus 2 equals to 0. So we have the corresponding roots, -1 and 2. Right? So in case this method doesn't work, we can move on to method 2 by applying the quadratic formula. So for a quadratic equation in the form of ax squared plus bx plus c, the roots of this quadratic equation can be written as follows. -b plus or minus square root of discriminant divided by 2a. The discriminant is simply b squared plus 4ac. So how can we solve the quadratic equation using this formula? Okay, so if we have x squared minus x minus 2 equals to 0, we can solve the quadratic equation like this, right? Putting the a equals to 1, b is -1, and c is -2, then we can make use of the quadratic formula to find out the same results, -1 or 2, as the roots of the quadratic equation. And finally, for method 3, which is to solve the quadratic equation using a graphical method. So if we are trying to solve the quadratic equation ax squared plus bx plus c equals to 0, then you can find the x-intercepts of the quadratic graph y equals to ax squared plus bx plus c. Okay, so this y, in step 3, I'm trying to plot the graph of y equals x squared minus x minus 2. Okay. Putting this in GeoGebra, then we have the quadratic graph. The x-intercept of the quadratic graph will give the roots of the quadratic equation. So we will have the solution -1 or 2. So these are the typical approaches that we can deal with the quadratic, so you can solve the quadratic equations. And the next thing to review is about some properties of quadratic graphs. So if we have a quadratic function in this form, y equals to ax squared plus bx plus c, then we have the following property. When a is positive, then the quadratic graph will open upwards and it will have a minimum point. Whereas when the coefficient a is negative, then the quadratic graph will open downwards and it will have maximum point. And anyway, the minimum point or maximum point of these quadratic graphs will occur at x equals to -b over 2a. Okay, so this is where the extreme point or the vertex of the quadratic function will occur. Right, so that's all for what I'd like to review, and we'll move on to the application problem sets. The first one, we are given the demand curve and the marginal cost of production. If the government wants to set a per unit tax such that the tax revenue is maximized, what will be the optimal per unit tax to be set? The key thing to recognize for this question is that the marginal cost of production is constant at $11, which means that we have a flat supply curve which is perfectly elastic. If we have a per unit tax of $T, then the price paid by buyers will increase by exactly $T. This is why the after-tax price paid by buyers becomes 11 plus $T. If we plug in this new price paid by buyers back into the demand curve, then we are able to find out the after-tax quantity. After some simplification, we have the expression 98 minus 2T as the after-tax quantity. Because we are going to find the point where the government's tax revenue is maximized, so this is why we would like to write out the tax revenue function and to find the value of per unit tax such that the tax revenue will be such that the government's tax revenue is maximized. So total tax revenue would be per unit tax T multiplied by the after-tax quantity. So we just plug in the after-tax quantity, 98 minus 2T, inside here, then we will have the expression. And you expand this, we'll have the tax revenue equals to negative 2T squared plus 98T. As we have just reviewed, the maximum point of the quadratic function occurs at negative b over 2a. So here, the so-called a is 2, whereas the so-called b is 98. So this is why the government's tax revenue is maximized at this point. The optimal per unit tax required is $24.5. All right, so what about the next problem? We are given a demand and supply function. If the government is considering a subsidy policy and has a budget of $5,500, what will be the amount of subsidy that the government can provide? So let's start with this problem. So because the government has a budget of $5,500, so this is why the per unit subsidy multiplied by the new quantity equals to 5,500. So this is the target equation that we would like to solve. The per unit subsidy of S can be expressed using the subsidy wedge, right? So how can I do that? It is simply PS minus PD, price received by sellers minus price paid by buyers. For the PS and PD, we can find them out by rearranging the demand and supply functions using P as a subject. So this is what I'm trying to do at the very beginning step. After that, we can put the supply and demand functions back into the expression of PS and PD respectively. And after some simplification, we will have the per unit subsidy S equals to this expression, Q divided by 500 minus 219 divided by 15. Okay. Now, per unit subsidy S is expressed in terms of Q. As I've identified, the target equation to solve is per unit subsidy multiplied by the new quantity equals to the subsidy expenditure, 5,500. So we just put per unit subsidy S back into this equation. Then we are able to solve this out because this equation has only one unknown, Q, to solve. And specifically, this would actually be a quadratic equation. Rearranging this a bit, we will have the quadratic equation in this form. Then we can move on to solve this quadratic equation out. And I will demonstrate the graphical method so that we can simplify our mathematical calculations. To solve this quadratic equation, I can plot the quadratic graph of y equals to the left-hand side here, okay, replacing q by x. And then we are able to find the x-intercept of this quadratic graph as the solution of q. This is what I'm exactly doing in the GeoGebra screenshot here to type the quadratic graph. Naturally, we have two x-intercepts for a quadratic function, and we should reject one of them in our answer. We should reject point A because we should not have a negative quantity. So this is why we should have a new quantity, 3,082 point something. Last but not least, we need to find the per unit subsidy required. Just plug in this new quantity back into the subsidy wedge expression that we have derived in the previous slide. Then we're able to find out the per unit subsidy is $1.78. Okay, so this is how we deal with the subsidy expenditure target. And the next question now, we have demand and supply functions directly given. And to maximize tax revenue of the financial secretary, what will be the per pack tax of cigarette to be imposed? So again, we follow something similar. We need to write out the tax revenue function and find the point where the tax revenue can be maximized. Okay, the tax revenue will be per unit tax T multiplied by the quantity. So this is the target function that we would like to express out. Nothing special. For the per unit tax T, we will use the PD minus PS, price paid by buyers minus price received by sellers, the tax wedge approach to express that. As we have explained in the previous question, we need to find PD and PS by rearranging the demand and supply functions using P as a subject first. And after that, we can express the per unit tax T equals to this ugly thing here. And this also put to replace the per unit tax T. And again, we have the tax revenue function put down here. We can find out the per unit tax that maximizes the tax revenue, which occurs at negative B over 2A. So we have this as the B and this as the A. After some simple calculation, we should be able to get that tax revenue is maximized at the new quantity, 20,238 point something. All right, so put in this new quantity back into the tax wedge expression that we have just derived. Then we have the per unit tax required, 86.65, and this per unit tax would maximize the tax revenue of the financial secretary. So to conclude, I have some remarks to highlight with you. So you need to make sure you understand when you are solving a quadratic equation and when you are trying to optimize a quadratic function. If the question asks you something like, oh, what will be the per unit tax that generate a certain amount of tax revenue, then you're actually solving a quadratic equation. Whereas in this problem, where you are finding the per unit tax that maximizes the total tax revenue, then you're actually finding the maximum point or the extreme point of the quadratic graph using x equals to negative b over 2a. So make sure you can differentiate under what situation you are solving a quadratic equation and optimizing a quadratic function. Right, so that's all for the coverage in part A. And the remaining time would be for part B to deal with quadratic functions in perfect competition and the treasury of the commons. We have a perfectly constant cost industry in this question. And if the price is less than how many dollars, a typical hotel will exit the industry. So we are actually finding the exit price of the industry. How can I do that? We will recall the exit condition, which is where marginal cost equals to average cost. All right, so this is why we are going to solve the equation where marginal cost equals to average cost. For the marginal cost, it's already directly given, so nothing worry about that. How about the average cost? We need to derive that from the total cost expression. Average cost is total cost divided by the quantity. So this is why we can obtain the average cost from dividing the total cost function by small q. This is exactly the expression that I have obtained here. All right, so putting everything back into the equation that we would like to solve, MC equals to AC, then we can obtain the result, and it is actually a quadratic equation again. So after some steps, you will be able to solve Q equals to 7.2526. We do not take the negative number because quantity cannot be negative. All right. So put this lower equilibrium quantity of an individual firm back into either the marginal cost or average cost expression, then we are able to find out the corresponding exit price to be 1035.26. Okay, so what I've just demonstrated is to solve this problem mathematically, because we are going to find a point where marginal cost equals to average cost, or equivalently, it is simply the minimum point of the average cost curve. We can do it in GeoGebra as well. As you can see, after typing the marginal cost and average cost function, and we can find out the intersection point between the two curves. The corresponding price or the corresponding y coordinate of the intersection point will be the exit price, 1035.26, the same number as we have obtained. All right, so hope you understand this, and we'll move on to another problem, which is about a monopoly. So we have the demand curve and the marginal cost. If the fixed cost of the monopolist is this amount, what will be the lowest price ceiling that can be imposed? So again, the key is that we do not want the monopolist to exit the market in the long run. So this is why we would like to find a point where the price equals to average cost, again, the exit condition. So for the price side, it can be represented from the demand curve. Whereas for the average cost, we need to derive it on our own. So how can I do that? Average cost is decomposed into the fixed part and the variable part. So we have average fixed cost plus average variable cost. Okay, so for average fixed cost, it will simply be the fixed cost divided by quantity. And for the average variable cost, it will be the marginal cost. Why? Because we have a constant marginal cost of $6. If we are trying to find out the total variable cost in this case, then it will simply be the area under the marginal cost curve until the quantity that you are looking for. So this is simply the area of a rectangle, calculated by marginal cost times the quantity. However, at the same time, by the definition of average, we also know that total variable cost is average variable cost times the quantity. So this is why when the marginal cost is constant, we will have marginal cost equals to average variable cost. We can now derive the average cost curve. Fixed cost is 29,645 and the marginal cost is 6. Then we will have the average cost expression here. Then we can move on to solve the equation that I've just identified. Equating the demand expression with the average cost expression, which is like here. And after some rearrangement, you are able to find out the general form of the quadratic equation here. 0.2 q squared minus 154q plus 29,745 equals to 0. And again, we can just plot y equals to the left-hand side of this quadratic equation in GeoGebra so that we can find the x-intercept of the quadratic graph. This time, we have an equal root at q equals to 385. So this will be the corresponding quantity due to the optimal price ceiling. Plug this quantity back into the demand curve, then we'll have the corresponding price or the required price ceiling, $83. All right, so what I've just demonstrated, again, is a mathematical way to solve this problem. However, actually, we are just finding the point where the demand curve and the average cost curve intersect each other. If we would like to simplify our calculations, then we just type the demand and average cost function in GeoGebra to find the intersection point. And again, we have the same result. The lowest possible price ceiling is $83. Right. And we'll move on to the last problem of this topic, dealing with the tragedy of the comments. We have 15 doctors living at the mid level of a hill, and they have two ways to go down from the hill, either by driving on their own or to take the tram. So from society perspective, what will be the number of doctors driving? So the decision rule is that we would like to have the total time of traveling down the hill by all doctors is minimized. If we can find out the total full cost of all doctors to travel down the hill, then we can find the minimum point of this function and to solve this problem. Okay, so this is the key. How can we do that? If there are n doctors going to drive, it will take each doctor 2n plus 4 minutes to drive, right? So the total time cost of these n driving doctors will be n multiplied by 2n plus 4. How about the remaining doctors who will go down the hill by the tram? It takes 12 minutes, right? And we have 15 minus n remaining doctors. So this is why we add the total full cost by 15 minus n times 12. So this expression will be the total time cost of all 15 doctors to go down to the hill, which is also put down in the next slide. After some simplification, you are able to obtain total time of traveling down the hill to be this thing. And for this polynomial, the coefficient in front of n squared is positive, right? So it should have a minimum point. It should occur at negative b over 2a again. So we will have the minimum point of this quadratic function at this number, equivalent as 2. This means that when n equals to 2, the total time of traveling down the hill for all 15 doctors is minimized. All right, so a remark for this problem is that because the value of n must take integer value, right? We cannot have like 3.14 doctors. So this is why we may need to do some kind of checking. In case the total time suggested here is not an integer, let's say you obtain 1.8, something like that, then you need to move on to check the integer around this number, round down and round up this 1.8 to find at which value of n such that it minimizes the total time. Specifically, you need to check the integer value around 1.8, which are n equals to 1 and n equals to 2, to see at which point it minimizes the objective function. But for the original version, there's nothing to worry about that because we can obtain an integer already. Yes, that's all for the discussion on quadratic functions and also the coverage of the refresher topics on mathematical techniques.